Hi there, my name is Christopher Wurst. Welcome to the first video of Homework 2 of Transport 1. This one's going over Part 1, which is saying a sealed cylindrical tank with height of 1 meter and cross-sectional area of AC equals 1 meter squared is filled with water to an initial height HI of 0.9 meters. The headspace above the water was initially at a pressure of 101,325 pascals, or 1 atmosphere. A hole the size of 0.001 meters squared is then punctured at the bottom and the water drains out. So part 1 is asking us to derive a differential equation for solving the height of water in the tank as a function of time, and then solve the problem numerically and plot the results using scipy.integrate.solve IVP and plotly respectively. And then as an initial challenge to this, it's asking us to also avoid round-off errors arising from simulation times extending beyond the steady state reached by the system using events features of scipy integrate solve IVP to terminate the solution when it calculates the velocity of the exiting water, and that velocity equals 0. So, as always, we're going to derive the equations first, and then we're going to use Colaboratory to plot it out. And then to start, I've got my whiteboard behind me. I'm going to start by drawing a picture. So, we've got to draw a picture. We have a tank of height capital H, initial of total height, filled to some initial height HI. I'm not going to use the actual values for height just yet. That will come in the coding. But we've then got an initial pressure up here. PI equals 101,325 pascals. Actually, let's note this as P1, and we've got a little hole down here, which water is draining out of, and we'll note that arrow as it's draining out. So we've got some pressure 2 out here at, this is open to the air, so it's again 101,325, and then we know that the initial pressure PI is also 101,325 pascals. Is there anything else we need? Yes, the area, we're just going to note this as area of hole, or A hole. Not shortening that for anything, but the area is equal to 0.001 meters squared. That's not a big issue. That is, yes, correct. Okay. And then the other thing that we need is, I'll draw a separate picture down here, small one, to note that this is a cylindrical tank, so it's got an area, a cross-sectional area of AC. It doesn't give us that, or it does give us that AC, but it's not useful right now. So, the big key to this entire homework is Bernoulli's equation. So I'll write out the long form of it and then shorten it to what we need for this homework. And I will then be using that specific version in all the later parts. So, Bernoulli's equation states that P1 pressure at state 1 plus 1/2 times the density times the velocity at state 1 squared plus rho GH height 1 is equal to P2. So the pressure at state 2 plus 1/2 density velocity at state 2 squared plus density times the gravitational constant times the height at state 2. I will also note that over here, hi and then h2 equals 0 meters, because this height is at the bottom, we're just going to make that 0. And then whatever height this drains down to will be h1, our initial height, plus frictional heating, which is a very fancy F. And then I'm going to move all of these across, or well, this comes into play later, but it's not actually in this equation right now. This will then go across to be, or actually we're going to subtract all of this across because we want P2, 2 minus 1. So P2 minus P1. So the difference in pressures between state 2 and state 1 plus 1/2 difference in velocities between state 2 and state 1. So V2 squared minus V1 squared times the density plus density times gravitational constant, difference in heights between the two, so h2 minus h1 is equal to, here comes the frictional heating. Now, you notice that these two have that. This, of course, equals 0. We're going to ignore that in this case, so I'm just going to cross that out. That's not useful in this case. So it's going to go to difference in pressure, P2 minus P1, so pressure in state 2 minus pressure at state 1 divided by the density plus velocity in state 2 squared minus velocity in state 1 squared over 2. This is also getting crooked. And then plus rho times gravitational constant, density gravitational constant, h height at 2 minus height at 1, difference in heights is equal to 0. Now, V1 is the velocity here, the velocity at which this water drains out. That is small already. It takes a while for it to drain. And of course, when you square an already small number that's less than 1, call it 0.0 something, that gets even smaller, so we're just going to assume that V1 is equal to 0, or V1 squared specifically is equal to 0. And then H2 is 0, we know, and then H1 is H1. So all told, for this equation, we're going to have, for this scenario, we're going to have difference in pressures, P2 minus P1. I'm also going to substitute in, I'll substitute in after. The difference in pressures between state 1 and state 2, so P2 minus P1 divided by the density of water, which is 1 or 1,000 depending on what units you're using. 1 gram per milliliter, 1,000 kilograms per square meter, I believe. Something around there. Plus velocity at state 2 divided by 2 plus rho g, this is actually minus rho g, rho g h1. So of course equal to 0. So we have all of this, but we don't know what yet we want to solve for. So the question specifically asks for a equation that will link the change in height with solving the height of water in the tank is a function of time. And to do that, we're going to look at flow rates. So Q, Q is equal to, it could be V1A1 or V2A2. V1 is gone, so we're going to call it V2A2. So velocity at state 2 times the area at state 2. Now, that gives us, and I'll write this up here, Q equals V2A2. This also goes to, because we know Q is the change, so we also know that negative Q is equal to, or specifically Q out, flow rate out, is equal to the change in volume over time, which then, because volume and specifically at state 2, the whole, no, the change in volume is the volume here, AC. We know that this cross-sectional area is constant. That means that negative Q out is equal to AC cross-sectional area times the change in height, dH, all over change in time. So that means that goes to negative AC change in height over time is equal to velocity at state 2 multiplied by the area of state 2, which is, of course, we know the area of the hole, which all told means that the change in height over time is equal to V2, velocity at state 2, times AC, the area of the hole, over the cross-sectional area, and that's negative. Yes, so that's what we want to find. And I will substitute that up there, and I will also write this specific massaging of Bernoulli's equation up here as well, to give myself more room and to know what we're looking at. So, again, change in height over time is equal to negative V2, negative velocity at state 2, multiplied by the area of the hole, divided by the cross-sectional area. And then we also know that transcribing P2 over P1 divided by rho plus velocity sum at state 2 squared over 2 minus density. No, density is not here. This is just G times H. Yeah, because this divides through. Almost missed that. Minus G times H1 equals 0. Okay, so I'm going to, now that that's been transcribed, this is not a great eraser. This is better. Oh yeah, that's much better. Erase all of that, got that transcribed up here. So now we know that we want V2 for this. So we've got V2 here. But we also have a couple of other variables that we need to solve for. Specifically, we know what P2 is. We don't know what P1 is. And H1 is, we don't need to solve for that because we're looking at the change in height. So that's fine. But we need to figure out what P1 is. So as you know, P1 is the pressure in the tank above the water. So what we also know is, oh dear. There we go. All right, fix that. We also know that it's given us a pressure, and air can be treated as an ideal gas. So another equation we're going to use is good old ideal gas law. PV equals nRT, pressure times volume equals the number of moles times the ideal gas constant, R times the temperature. This means that given an initial headspace of air, there must be a constant number of moles. So there's also, I'll make an arrow in here, and number of moles, N. So we're going to be using N in both because N is constant in both the initial state and the changing state, we can find N in both states equivalent, make them equivalent, and use it to find P1 in terms of the initial pressure, which we have a value for. So, we know that P1 volume 1 equals NR temperature 1, and then we also, this is for the, I'll make a note, changing, and then initial state, Pi, Vi equals nRTI. So, let's start with the initial. This is going to go to P, pressure initial volume over R initial temperature equals N. We know what the initial pressure is. The initial volume is, of course, this difference between H and HI multiplied by the cross-sectional area. So again, height times area. So this actually goes to, I'm simply going to move it down to give more space for this one. Down to P initial pressure times cross-sectional area AC times capital H, height of the entire tank minus initial height all over RT, and we're going to assume that the temperature stays the same. So these two, I can erase their little notes there because there's no difference between states. Equals N equals. So we have a moles here, and then let's do the same thing over here. So pressure in state 1 times volume in state 1 all over ideal gas constant times temperature is equal to moles, goes to, now this is, the volume here is different from the volume in the initial state because HI is no longer the height. So that's just going to be H, the total height, minus H1, the initial height, or the height at state 1. So that goes to P1, cross-sectional area again, height of the total container, minus height at state 1, all over RT. Now, H1, we could call it just H as the actual height, but H1 works. Height at state 1 equals N. So, let's get these, make these go together. I'll make two arrows kind of pointing at where we're going. So N equals N, of course, number of moles is constant, so pressure at state 1 multiplied by cross-sectional area, H, height of total container minus the height of the water level is the volume of the air as it changes, divided by, of course, R, the ideal gas constant times the temperature, and then the initial state, the initial pressure times the initial volume, cross-sectional area, height of the total height of the container minus the initial height of the water divided by ideal gas constant and temperature. Of course, these two are the same, so if we were to multiply across, which we will do, we would cross out all of the constants. It goes to, we want to find for P1 to substitute in here goes to P1. The pressure at state 1 is equal to Pi, the initial pressure, times H, the the initial height difference divided by the changing height difference. So let's move that back into here. I'm going to write this up here so we can have more room and erase all of this. So we know that pressure at state 1 is equal to initial pressure, initial height difference divided by changing height difference. And then let's erase all of this, and we are almost finished. So we're going to bring this bad boy back down. This goes to pressure at height 2, pressure at state 2, minus pressure at state 1, divided by the density, plus the velocity squared over 2 minus gravitational constant times the height. And then we can substitute in goes to pressure 2 minus the initial pressure multiplied by the initial height difference divided by the changing height difference divided by density plus the velocity at state 2 squared that we want to solve for divided by 2 minus gravitational constant times the height equals 0. I'm going to move all of this over, goes to be easier if we can do just this. V2 squared over 2 is equal to, this moves over and is negative, so these two flip, goes to pressure, the initial pressure times initial height difference divided by changing height difference minus pressure at state 2 divided by the density plus gravitational constant times the height, and then we will multiply it by 2 and take the square root, so V2 equals the square root of 2 multiplied by everything, so Pi initial height difference divided by changing height difference minus pressure at second state plus change in, or plus the gravitational constant times the height. And now that we have all this, we could leave it there. But something else to note is that both the initial pressure and the pressure at the second state are the same, so we can make this equation a little bit less ugly, we'll call it. So this can actually go to, one more time, V2 is equal to square root of 2 multiplied by P1 and P2 are the same thing, so 101.325 pascals over 2, over velocity. No, over density, there we go. Density multiplied by the change in the initial height difference divided by the changing height difference minus 1. Yep. Plus the gravitational constant times the height. And that is V2. So with that being created, we know what this change in height is. And you know what, just for completion's sake, I will write it through, but in the code, we're just going to make a function and then plug in V2. So all told, going to need to do a little bit of a squat to make sure that this is straight. The change in height over time is equal to negative the square root of, we'll call it 2gh, just to make sure, gravitational constant times the height plus 101,325 over the density times initial height difference divided by changing height difference minus 1. And then here multiplied by the area, the difference, the area of the hole divided by the cross-sectional area of the tank. And this, or well, this and this is what we are going to plug into our coding, which we will get to right now. All right, so now that we've got our co-laboratory script open, I have notes over to the side here of the equations that we're going to be using. They worked out earlier. Let's begin. A little refresh, we want to solve the problem numerically and then plot the results using scipy.integrate.solve_IVP and plotly respectively. And then it asks us to use solve IVP events to terminate solution when the velocity reaches 0. So to start, we're going to start importing what we need. We want import numpy numerical Python as np, as a shortener. We want integrate dot solve scipy.integrate.solve_IVP from scipy scientific Python import scipy.integrate solve_AP. Probably just scipy.integrate. We also want plotly, so import plotly.io as PO from plotly import make subplots, and then we want to make our subplots dark mode because we don't want to hurt our eyes, and just as a little preference, so plotly template default equals shift enter. Now from scipy.integrate import solve IVP. Try that. Cannot import make. Oh. Awesome. Oh yeah, poly.subplots. There we go. Okay. So all that we really need to do right now is to define a function to take our right hand of the equation that we solved earlier for V2. Here it is. The V2 equals the square root of 2 multiplied by the gravitational constant G times the height H plus 101,325 pascals divided by the density multiplied by the total height of the container minus the initial height divided by the total height of the container minus the changing height minus 1. So we just want to define a function, we'll call it IVP, initial value problem, right hand side. We want to, so these, specifically solve IVP, likes to take vectors as its input. So we need a vector, just call it vec, and then t as its second variable. All we need here is height, so h will equal vec 0, i.e. the first value and the only value in vec, the vector variable. And then all we need is v2 is equal to, we'll call it lowercase v. v2 is equal to numpy dot square root of the 2 times g times h plus 101. We're actually going to want, 101,325 divided by the density, so rho multiplied by h minus hi divided by capital H minus lowercase h, our vector, and then minus 1. Okay, so we have all of that, and we can return what we want out of this function, or we want to return the changing height over time, so negative v2 times area of the hole divided by cross-sectional area AC. Enter. Okay. Almost forgot something. Now, as you most likely know, you can't have the square root of a negative, so in order to make sure that no errors occur during any of our calculations, we want to take the absolute value, np.abs, and then just add another parentheses at the end. Now we're going to be adding in our variables here. Let's start with the density. Rho equals, this is water, 1E3 kilograms per cubic centimeter, so kg per centimeter, or that should be cubic meters. And actually, just to make sure that in case any of the pressures are actually changed, we'll make this the external pressure there. So rho, let's actually start with the gravitational constant. G equals 9.81 meters per second squared. Let's do the external pressure equals 101,325 pascals, and making comments of these just for units, just so I know what any unit conversions. We need initial height or total height h, which I believe is 1 meter. Yes, 1 meter. That period after the 1 is to make sure that it is not that it's a float value, not a integer value, just in case any calculations change about it. It can get a little funky with it. Either way, hi is the initial height. I believe that is 0.9 meters. Let's double check that. Yes. And then the cross-sectional area of the hole is equal to 0.001 meters squared. And then the cross-sectional area of the entire thing is 1 meter squared. 0.001. Yes, okay. AC is equal to 1 square meter. All right, we have all of that. So now we have all of those values, and there's something that, if we were to plot this out as it is right now, we also want for future reference, an end time, just for later. We'll call that 10 seconds. That's for later. That's not overly important right now. But if we were to run this as it is right now, it would feasibly work, but it would descend in what would be a negative exponential graph, and then after a while start coming back up. So we don't want that. So what we want to do is, as the homework suggests, to create an event for solve IVP to stop, to terminate, right as the velocity hits 0. So I'm going to add a space for the code. We're going to define another function called v20, shorthand for velocity 20. We'll call it event. We also want another vector, and we want time as well. And pretty much what we're just going to do is copy over the calculations done up here. Control-C, Control-V. We don't need the absolute value because this is going to stop when it's 0. So get rid of that. We want to return the same thing. Control-C. Actually, no. We want to just return v2. And then at the end, after this, we want to do v20 event dot terminal equals true. Shift enter. Okay, no errors there. So that means that when this hits 0, it will terminate. So with that being said, we can do the solve IVP. So we're just going to call it result. Res equals solve IVP. We want our function, so we have IVP right hand side. We want our time span. We have 0 to our specified end time t end. We want our y value, which will be, we'll start with a vector of hi, the initial height. We want a method. We like to use redout. It's quicker and it gives a very good, clear resultant. And then we want to throw our event in. So event equals v20 event. Actually, I want this in brackets. And I also want a dense output to equal true. There. And do that down. Just enter. Float object not acceptable. Uh-oh. Let's try events. No, float object is not subscriptable. What does that mean? 0.9. Oh. You actually want t, then the vector. Time is always first in solve IVP. Try that. Too many indices for array. Diff. That's odd. Events v20 event. Try making it an array. no. That didn't work. So I return that. Might be this. I believe needs a vector. Runtime warning, invalid value entered in square root. This is separate from the Also, just little note. There's no need to have that be a vector. Assign a variable to that. Invalid value. Let's try res. What happens? End of the integration interval. Well, that's not good. We want it to terminate. What's this giving me? Invalid value encountered in square root. Which square root? Can't be that. So it's this. Let's try this. If the square root is giving me a problem, delete the square root. And it fixes it all. Of course it does. Okay, so what happened there was that we were getting, as I mentioned earlier, and what the absolute value in the right-hand side code is meant to do, or meant to get rid of, we were getting a negative in a square root, which we don't want. So now that we've gotten rid of that, we have our the resultant is correct. It's giving us the termination event occurring, which means that this event worked. And all that we need to do now is to plot it. So let's do fig equals make subplots. Fig dot add scatter. X equals, we'll do I want to make a time frame for this first. T plot is equal to, so the time for the plot is equal to numpy.linspace. We want to make this linearly spaced, a linearly spaced array of time points so that it will iterate and calculate the y value, i.e. the height, over, I don't know, 500 points of time. So we're going to start at 0. We want to go to the event, the end of the event, so we'll call that v20 event 0, 0 with 500 values. Now that we have that, we can put that into the scatter plot as our x-axis. Y will then equal res of solve for the t-plot. That should be all we need. I'm getting an error. Function's not scoped. Maybe not. Instead of this event, we want resultant, because this holds all of the events here. Dot t events. Whoops. 0, 0. This will give the first value of the events, i.e. This v0 event, which will then stop the gives the time for it. So res.tplot, and then we want first value from that. So no, Float object cannot be read. Float cannot be interpreted as an... Oh. Duh. It won't say him. Okay, that one was pretty simple. It just wanted me to delete this dot, and we'll get the same error. 2, because this is 500 point... It's interpreting as a decimal number, a float number, when it wants an integer, and it needs an integer because you can only have so many points or divide by so many points. So either way, with all of that out of the way, we now have our thing terminate at a specific point. We know that res gives a y array at a specific time 4.56 seconds when the velocity goes to 0. The velocity hits 0 and the height in the of the water in there, or the liquid in there, is 0.891 meters. And then we have the plot here, which shows that. With all that done, thank you very much for watching. I hope you have a wonderful day.